So welcome back to the afternoon session of the workshop. So this session we will have two presentations. The first one will be given by Professor Nicolas Rimbert on secondary automation. And Nicolas Rimbert is assistant professor in Henry Poincaré Nancy University. His research interests are turbulence, multi-phase flows, and droplet combustion. Now I request Professor Rimbert to give his presentation.
Thank you. Firstly, I am honored to replace Professor Soshka, who could not attend. And it won't be a full review on secondary breakup. It's more I will share my thought on the subject. There will be a review part, but it's not all that have been known that I will be present. So let me recall, some slides are very pedagogical, so let me recall the few numbers which are used in atomization. In classical fluid dynamics, we use the Reynolds number, which is the ratio between inertia and viscosity, and the Weber number, which is the ratio of the inertia and surface tension. But strangely, in atomization, we don't use these two numbers. Yes, I must go quicker. We use the Onser's number, which is the ratio of the Weber number, the square root of the Weber number and the Reynolds number. Most of the time, it's Onser's number and Weber number. So it's a kind of a change of basis. We don't use these two bases, but these two. And we'll see that it has some importance in the following section. There is a classical distinction between primary atomization, secondary atomization, and tertiary or other kind of after atomization. Most of the time, it's when the bulk of the liquid is breaking, it's a primary atomization. When the droplet generated by primary atomization, it's secondary atomization. And then you could have third order atomization. But most of the time it's unseen. There are some reports that when you have very high Weber number, you have catastrophic breakup and you can have third order atomization or fourth order atomization. But as far as I'm concerned, I did not see it. So I will focus on the secondary atomization, but it's a kind of artificial distinction. And I think that the same reasoning could be made at each step. Atomization is most of the time thought to be related to instability of the bulk of the fluid, and here are two classical instability. The first one is a Kelvin-Helmholtz instability. You have a difference of velocity between the air and the water, so you have waves. And what is important here, it's a Venturi effect. Once you have a small bump, you have pressure is decreasing over the bump because the air is accelerating, so it draws the liquid upward. So it can be related to Venturi effect. And another important instability is Rayleigh-Taylor instability. You have water, air, and here. And here you have the water which is flowing into the air. And you can make some computation and have the growth rate of the instability as a function of the wave number. Here it's a very simple without viscosity or surface tension relationship. But here are two fundamental mechanisms which may be responsible for the atomization process. So I will focus on the Rayleigh-Taylor instability in the following part of this talk. And I won't focus on the Kelvin-Helmholtz part, but I think that there are a lot of things to do here too. So now let us recall some very famous experiments in atomization and secondary breakup. As far as I have been able to find it, the oldest study I found were by Horvender in Germany in 1919. He studied drops. He took photograph of rain droplets, and then he draws this picture from the photograph. And here you can recognize what is called a back breakup. First, you have the drop which is flattened, and then you have an instability. and then the bag is created, the bag breaks, and then the ring is breaking. And during these experiments, he found a criterion for the stability of the droplets, and this criterion involved what is now called the Weber number, and so he found a critical Weber number of 14. Few years, 70 years later, Pilch and Erdmann in a landmark paper made the first classification of the different mode of droplets in secondary atomization. They found that, actually, I'm sorry, it's still in French. I forgot to translate all the. So you have first the droplet is stretched, and you can have some separation by stretching. And when the Weber number is increased, and this value, they can be discussed, but the hierarchy is okay. Between 12 and 50, you can have a bag breakup. Between 50 and 100, you have umbrella breakup. It means that here you have a stamen inside the bag. And when you go further, between 100 and 350, you have shear breakup. It means that you have a shear layer here on each side of the droplets, and you are eroding the droplets by the side. And if you increase again, it's very difficult to know exactly what is happening, so it's not very sure. But you can have a mix between instability and shear, and the way the mix is made is not very, very clear for the time being. The next step was work done in Michigan by Faith Group in Ann Arbor, and they studied either using drop tower and falling droplets, or using a shock tube and sending shock waves under the droplets. They made this kind of classification. Here you have the Weber number, here you have the Unsurge number, and they found that the bag breakup regimes was limited. With high Unsurge number, you cannot have very high Unsurge number for bag breakup. And then multimode breakup is, you have a lot of different classification. Here it's one example. And here the shear breakup is around 80 for the Weber number. And then you have several way of looking at this from an experimental way of. But what I would like to show next is that we can construct this diagram, making very simple physical reasoning, and it may give a new insight on what is happening in this region. In the same report, Professor Faith with Shu, for instance, reported that here you have the atomization speed as it's non-dimensionalized by a characteristic time I will show you next. So you can see that for shear breakup, here is the volume of atomized fluids. So you can see that the velocity is relatively constant, because here you have the cumulative removed volume percentage. So you are removing volume at a constant rate. Here it's for shear breakup. The same measurement has been made for bag breakup, and you still have something which is reasonably constant. And then you have big peaks during the breakup of the basal ring. So what we can say is that the erosion speed can be thought to be relatively constant. As for characteristic time, they have been mostly introduced by Ince in the 50s. He made a very crude reasoning. Here you have a droplet in a flow. You have pressure upwind and pressure downwind. And by making the difference between the pressure upwind and downwind, you can have the strength acting on the droplets. And then he considered the displacement of the droplet using a Newton's third law. And then you get this displacement. And this introduces a characteristic time, which is named T star here. And end of secondary atomization occurs mostly when you reach 5 to 6 T star. You can find it here by when 5, you can say that it's the end of the atomization. Another important characteristic time introduced was viscous time of, here you have the inertia of the gas, and here the viscosity of the liquid. So he showed that when the liquid was very viscous, for the atomization may be limited by the time for the momentum in the gas to penetrate inside the droplets. So introduce this second viscous time. Actually, I will use another time which is very, very close to this time. And the third time, which is very important, is the Rayleigh characteristic times. It's the time characteristic for the oscillation of the droplets due to surface tension. So here I have some few video from Professor Joseph, which I show because they are pretty. So you can see that it's for very high Weber number. So we are slightly over the back breakup, or even largely over the back breakup. But you can see that when it's becoming very viscous, the behavior is a bit different, but still similar. And you can see that you have wavelengths. So you have first deformation into a spheroid, a disk, kind of disk. And then you have instability growing on the disk. And this is this kind of modeling I will use in the next part. And here you have a viscoelastic fluid. So you can see that the behavior is very different when you have viscoelasticity. So that was the main motivation of Professor Joseph, I think. So now I will focus on the way of modeling this secondary atomization phenomena. The classical way is named the TAB model, TAB model, for Taylor analogy breakup. So as part of this review, I will try to show the reasoning behind this review. The idea of O'Rourke and Amsden was to introduce the oscillation of the droplets. And so they made an analogy between a mass spring and dashpot oscillator. And they had to identify the mass of the oscillator. The exterior force was the force created by the airflow. The viscous damping is here, and here you have the oscillation. The spring is actually the surface tension of. So they made some dimensional identification, which introduced some parameter to be fit, and they found that they could find some experimental results by fitting this parameter. Then you can try to have a solution to this equation. So here it's made in a non-dimensional form. So it's written in a non-dimensional forms. And they have a breakup condition is when the amplitude of the oscillation is of the same order of magnitude as the radius of the drop. You have a breakup. So it can be written this way. And you have a breakup condition which introduce, you see the ratio Weber number over 12, which is the value which is assumed to be valid for the beginning of the back breakup. Actually, this is a very crude modeling because it's it's an analogy model. It's not drawn from physical law. It's you make analogy and you want to have something, you obtain something, but I'm not sure it is as valid as other model. I will show you why in the next slide. What is important is that the breakup characteristic time is Taylor times, approximately, in this modeling. And that you can recover in other modeling. If you look back at back breakup, here I detail the 6th stage. First, you have a deformation. And this deformation you have a very flat disk. A very flat disk is very different from this kind of, here you have a linear oscillator, which is only valid for very small oscillation. When you can make you have better things than that. You have a lot of paper in GFM in the 70s or 60s when they made a very linearization of the oscillation of a droplet. And, but I don't think it still does not work because your droplet is becoming very flat. So you have to find something which is valid even if the droplet is very flat. And then on this disk, you have wavelengths of Rayleigh-Taylor instability, which are building. This creates the bags, and then the bag is breaking, and the ring is breaking. So I will focus on the four first steps. Actually, the first step will be modeled using the droplet deformation and breakup model of Ibrahim and co-workers. And the second step, it will be modeled using Rayleigh-Taylor instability. So in the Ibrahim, Young, and Prescas made a model named the droplet deformation and breakup, which gives the deformation ratio of the droplet. Here you have the, they suppose that the droplets deforms into a spheroid. A spheroid is an ellipsoid, kind of ellipsoid, but very symmetric. Here you have the great axis of the big axis of the spheroid, and they found that the breakup occurs when the great axis of the initial ratio, that is the deformation of the droplets, was about 2. And they could find the end of at the end of the deformation, the equilibrium deformation was given by this equation. Actually, this equation comes from this more intricate equation, which is a nonlinear oscillator of the same kind as the Taylor analogy breakup, but it's derived from the from the physics, the exact physics of the droplet deformation. Why? Because they made an energy conservation consideration. So it's very similar to what you make in analytical mechanics when you are using the virtual power principle. Here it's a computation of the exact energy variation around a path of deformation. This path of deformation is you need to have an ellipsoid. It's not true if it's not an ellipsoid. But if it's an ellipsoid, this equation is exact. That is why, as far as I'm concerned, I think it's the most interesting to use. So the problem is that it's nonlinear. So it's very difficult to say something about it. So what did I do? I linearized this equation around the spherical shape. And doing this, I have some parameter which appears. And then I have to consider a linear oscillator first by the airflow. And you will have oscillation or not. Actually, you will have oscillation if this discriminant is negative. And when you look at this formula, it introduces two characteristic time. The first one is very well known because it's Rayleigh characteristic time, and the second one is nearly the In's characteristic time. So, but the difference is that no, it's not the In's characteristic time. I'm sorry, but it's a viscous characteristic time still. So it's a time for the momentum to penetrate inside the droplets. It's not In's characteristic times. When you do this, you have oscillation frequency, which appears. You can introduce the ratio between these two times. And this gives you, actually, the ratio between these two times is the famous unsurge number. And when this unsurge number is equal to a critical value of the unsurge number, equal to 1.44, then you have the transition from oscillation to non-oscillation. And the frequency of oscillation is given by this kind of critical behavior when you are closing to the critical unsurge number. And, but if you are far away from this critical Weber number, the characteristic frequency is the inverse of the Rayleigh characteristic time. If you make the same things using a TAB model here, you find that the critical unsurge number is not a constant. Here it's a constant. It's the same for all fluids. If you make the same reasoning with TAB model, it's different for every fluid. So I think that the DDB model is a good way of doing this kind of reasoning. So I can begin by building the diagram now. You have a transition from oscillating droplets to non-oscillating droplets around 1.44. If you don't have oscillation, it will be very difficult for a Rayleigh-Taylor instability to work because the instability will be dumped very quickly. So here you are in a stability region as far as Rayleigh-Taylor instability is concerned. The wavelength of the related instability is given by this formula. Here you have the surface tension, the difference of density between the liquid and the air, and here the acceleration of the droplet. But when the droplet is falling, the droplet is decelerated, and you can have a classical formula for the drag of a droplet. But here we introduce the drag of a deformed droplet, so it's a bit different. We'll have to take into account the drag coefficient of the deformed droplets. When you put this into this, you obtain this formula, and you have the ratio between the wavelength of the related instability to the size of the initial size of the droplets. In the paper of Pilch and Erdmann, they found that the CD was 1.7 for falling droplets, and I use the 3.0, but it's more like 2.5 for shock tube. But they also mentioned this value. So at the beginning, I used this value. So next, I can use the criterion made by, in the DDB model, is that you break up when your deformation is equal to 2 times the initial radius. And then I want to have exactly 2 wavelengths on the droplets once it's deformed for the back breakup to occur. When I made this equation, and I put it back into this formula, I obtain a critical value for the Weber number for this instability to occur. So you see that this critical value for the Weber number is related to the drag of the droplets. So if I use the free fall drags, I obtain 23. If I use the shock tube drags, I obtain 30. So I can recover some value which has been published in the literature. I think that Inns has found this value. But thereafter, a lot of other experimental works have been done, and some value may be different from author to author. Another interesting thing is you can consider what happens when you have 3 wavelengths. Actually, when you have 3 wavelengths, you will have a stamen inside. You have the umbrella breakup. And the relationship is that on the radius of the deformed droplets, that 2 times the greater semi-axis. You have 3 wavelengths. And if you use this equation and put it back, then you have this new value for the critical value of the Weber number. Here it's for free fall. So it means that for free fall between 23 and 52 with this analysis, you have a back breakup related to the creation of 2 wavelengths. This can be, so here is the conclusion. And another thing is that you can consider that inside these droplets, here you have 2 inflection points on this curve, and between these 2 inflection curves, the inner part will go into the bag, and the outer part will go into the ring. So you can make, by making a 1D axisymmetric consideration, you can say that 1/4 of the liquid is going into the bag, and 3/4 of the liquid is going into the ring. And what has been reported experimentally is that 80% of the liquid is going into the ring. So you can make a branching ratio. You can say this portion of the liquid is going into the ring, this other portion is going into the bag. And if you make a mass balance, you have 5 to 6 droplets which are going to go into the ring. For 1D, the reasoning is a bit different in 1D or in axisymmetric 1D. And it's agreed with some report on the wound jet in a cross flow by these authors. So you can have another step into the building of the diagram. And the damping factor appears to be just the ratio between the unsurged number and the critical unsurged number. So you can see that this rise time is becoming imaginary if you are over the critical unsurged number. So you don't have, this is a case where you don't have oscillation anymore. Comparing this rise time to the characteristic time of growth of the related instability, which is given by this formula. Here you have the acceleration of the droplets. So I can use back my formula, and I have this big formula which I simplify by introducing this parameter. You can see that the characteristic time of growth of Rayleigh-Taylor instability is proportional to the Rayleigh characteristic time, and there are some other factors depending on the Weber number. It's the same here. Here, you introduce actually the characteristic time of Rayleigh. So by making this comparison, I want to have a rise time quicker than Rayleigh-Taylor growth time. This is this condition, which turns to this condition between the growth rates. And since the Rayleigh time is the same, you can simplify, and you obtain this final relationship, which gives you the area where you will have deformation quicker than Rayleigh-Taylor growth. But this constant here is very dependent on the Weber number because it depends on the drag coefficient, and the drag coefficient depends on the deformation of the droplets. So by using this empirical from phase and or and introducing it back, I can set an uncertainty number, define the final deformation as a function of the Weber number, define the drag coefficient as a function of the deformation, use this to compute K, and then find the limit as a function of the Weber number. So here you have the deformation. You can see that for very high Weber number, you don't have any more slow deformation. The deformation is about the same characteristic time as the Rayleigh-Taylor growth. So, and here you can see that I've made another classification rather than use back breakup, umbrella breakup, and so on. I use one wave breakup because you could have just one wave inside the droplet. You have two waves breakup, three waves breakup, and you can see that in this area, you still have faster deformation than the growth of the instability, so my computations are exact. But if I go outside this area, then I have a too slow deformation, so I don't have a disk. I have something which is not a disk when the instability is growing, so my computation won't work anymore. But what is very strange is that if you look at this limit here, it's around 80 for the Weber number. At most of the time, it's around the same zone, the same kind of value that is used to distinguish between the back breakup and the shear breakup. So it means that shear breakup must appear in this slow deformation area. Here, I'm not sure how long do I still have?
5 minutes more.
5 minutes more. Here, actually, this reasoning has been published nearly at the same time by Wei Zhao, which is a Chinese PhD student, and myself and a colleague. And, but we had made some very small difference in the reasoning, where Wei Zhao and co-worker considered one wave breaking. So I was wondering if the initial condition may, on the droplet deformation may impulse a change on whether you have one wave or two wave breaking. And if you look at other works by Professor Faith and Xiang, he says that on this in this line, above this line, here you have Reynolds number, Weber number. Above this line, you have an initial deformation which is ball-shaped. And here under this line, you have an initial deformation which is dome-shaped. So the initial shape is different whether you are above this line or not. So if you have a dome-shaped, you can have a one-wave deformation because here it's flat, so you can reconnect the deformation using just one sinus. And if you have a ball-shaped, you can imagine that you have a two-wave deformation. So this may help in distinguishing between these two. So I'm not sure for this last part that it is very, very, very useful. Here it's back on the diagram. How does it change? Here on this part you should have a dome initial deformation, and here you have ball initial deformation. So it's some kind of important still because, as I said, DDB model, you have to have a perfect ellipsoid for the equation to be exact. So if you have a dome, it's not the DDB model that should be applied. And if you have a ball, it's another model still that should be applied. So this may create some change in this classification. Here you can see the same classification, but for shock wave deformation of the droplets and not free fall. So here is the conclusion. You have a new way of looking at back breakup. You have a competition between instability and deformation. It's help in establishing a theoretical diagram. I think that maybe having this diagram in mind and making the experience again, you can just look if it's true. Maybe it's very simple, so it may not be true, but it gives you some clue, some way of looking at the experiment. For instance, do we have this part? You see that in this part, there seems, for very small value of the uncertain number, the area where you have slow deformation and fast deformation seems to be much for lower value of the Weber number, you can have both effects. Alors, is this part true? So having a new look at the experiment may explain may help in explain if this deformation, if this diagram is true or not. Lastly, the dome ball transition may help in understanding the discrepancies between Huizao and coworker works and how it works with Guillaume Castanet in Nancy. And lastly, I did not speak at all about shear breakup. I'm sorry, but I did not have time to introduce it. But I think that shear breakup must somewhat be related to Reid's, Professor Reid's wave model and to the Kelvin-Helmholtz instability. So maybe this way of reasoning can be extended to the Kelvin-Helmholtz instability and to the Professor Reid's wave model. So,
Thank you, Professor Rimbert. We will have time to ask 2 questions.
Two-wave deformation and three-wave deformation, right? So what happens to if it is more than 3?
Actually, if there is more than 3, I think you begin to have a mix between shear breakup and Rayleigh-Taylor breakup. So if you look at the video by Professor Joseph, you can see that you have waves, and at the same time you have shear. So you are in the multi-mode breakup, and my analysis does not apply because I did not consider Kelvin-Helmholtz instability or the shear layer which is formed around the droplet.
But in real situation, you need to consider both.
Yes, I think so. Except for very small velocity, for Weber number under 100, you don't need to consider to.
How relevant are regime charts like that, which are built on single drop breakup studies, to a real spray?
Yeah, that's a good question because I think that the main part is the primary atomization. The secondary atomization does not contribute much for the way the atomization is.
So if there are no further questions, let's thank Professor Rimbert.
Thank you.